Okay, photochemistry and catalysis. The branch of chemistry that deals with the chemical action of light or the study of chemical reactions, isomerism, and physical behavior that may occur under the influence of visible or ultraviolet light is called photochemistry. Example, photosynthesis. Carbon dioxide in water reacts in the chlorophyll in presence of light and produces glucose and water. Lumber's in Beer's law. Lumber's states that when a monochromatic light radiation is allowed to pass through a observing light, the rate of decrease of intensity of radiation with thickness of the observing medium is proportional to initial intensity of incident radiation. Mathematically, minus di over dx proportional I intensity of incident light in its thickness. Okay, we can write removing the proportionality and minus di over dx equal to ki. Proportionality constant where di is the small decrease of the intensity of light, dx is the thickness of the medium, k is the proportionality constant, that is the absorption coefficient. When x equals 0, then I equal to I naught and on integration 0 to I minus di over I naught equal to 0 to x k dx, so log e I over I naught equal to minus kx. So I over I naught equal to e minus kx. I equal to I naught e minus kx, where I and I naught are the intensities of incident and transmitted radiation. Beer's law states that when the monochromatic light is allowed to pass through a solution, the absorption of intensity of radiation is directly proportional to the concentration of solution. From Beer's law, mathematically, log I over I naught proportional Cx, log I over I naught equal to Ecx. C concentration in molarity, E molar absorption coefficient, fraction I over I naught is known as the transmittance. So Lumber's Beer's law is combined state when a monochromatic light radiation is allowed to pass through a solution. The observance A of solution is directly proportional to the concentration and part of the solution. Fluorescence, there are certain substances when exposed to light or certain radiation immediately starts re-emitting the energy. So substances are called fluorescent substance and phenomenon is called fluorescence. This phenomenon is widely studied in physics, chemistry, biology, and material science. Example, organic dyes, calcium fluoride. Characteristics of fluorescence, excitation and emission. The substance absorbs energy from an external source, often UV or visible light, exciting its electrons to a higher energy state. As the electrons return to a lower energy state, the substance emits light at a longer wavelength. Stokes shifts the difference between the observed wavelength, excitation wavelength, and the emitted wavelength is called the Stokes shift, and emission always occurs in longer wavelength, lower wavelength than observed light. Fluorophores, substances that exceed the fluorescence are called fluorophores. Common examples of include organic dyes, example fluorescent, aromatic compounds, and certain proteins, green fluorescent protein. Application of fluorescence, analytical chemistry, detection and quantification of substance through the fluorometric techniques, biological imaging, visualizing cellular and molecular structures using the fluorescent markers, medical diagnostics used in the diagnostic assays like the fluorescence in the situ hybridization and immunofluorescence, environmental monitoring, detecting the pollutants in water and air, and material science studying the properties of materials like quantum dots, polymers, and nanoparticles, forensics and detecting latent fingerprint and biological traces. Phosphorescence, there are the certain substances which continue to glow the substance even after the existence of light is cut off. So substance is called phosphorescent, and the phenomenon is called phosphorescence. For example, zinc sulfide, The process of releasing energy relatively slowed in it is observed in the form of the light is known as the fluorescence. Example include glow in the dark stars, some safety signs and glowing faint. Characteristics of fluorescence delayed emission. The glow persists for a noticeable time after the excitation stops, ranging from milliseconds to hours. Materials common phosphorescent materials include glow in the dark paints, certain minerals, and organic compounds with specific structures. Energy state it occurs when the electrons transition from higher energy triplet state to a lower energy state. This transition is quantum mechanically forbidden, which caused the delay. Application of phosphorescence, glow in the dark, products, toys, watch, and safety science, scientific imaging and analysis, studying the biochemical process. Thermochemical reaction, the thermochemical reaction is a chemical reaction that involves the absorption or release of heat energy. It is characterized by change in the enthalpy, which is the total heat content of a system. The heat change associated with the thermochemical reaction is typically measured under the constant pressure and is expressed in terms of enthalpy change. Thermochemical reaction can be classified into two main types: exothermic reaction. This reaction releases heat to the surroundings, resulting in the negative enthalpy change. Delta S is less than zero. An example is the combustion of fuels such that burning of methane. For example, methane reacts with the oxygen, that is the burning, and produces carbon dioxide in water and heat. Endothermic reaction, this reaction absorbs heat from the surrounding, resulting in the positive enthalpy change. Delta S is greater than zero. An example is the thermal decomposition of calcium carbonate. Calcium carbonate is burning in calcium oxide and carbon dioxide. Photochemical reaction is a chemical reaction initiated by the absorption of energy in the form of light. Uh, Carbon dioxide in water reacts and produces to the glucose in the endothermic reaction. In the presence of light, it produces the glucose. Difference between the thermochemical reaction and the photochemical reaction and thermochemical reaction, the reaction involves absorption or evolution of heat, but photochemical reaction is the reaction involves absorption of light radiation. The reaction can take place in the dark as well as in the presence of light is the thermochemical reaction, but photochemical reaction takes place only in the presence of light. Temperature has a significant effect on the rate of thermochemical reaction, but in case of the photochemical reaction, temperature have very little effect on the rate of photochemical reaction. The value of delta G for a thermochemical reaction is always negative, but the value of delta G for a photochemical reaction is always negative or positive. The thermochemical reaction not selective in nature. Thermochemical reaction is not selective, but photochemical activation is selective in nature. Basic laws of photochemistry. There are two basic laws governing the photochemical reaction: the Grothus-Draper law, the Stark-Einstein's law of photochemical equivalence. Grothus-Draper law, it states that it's only the observed light radiation that are effective in the producing a chemical reaction is the Grothus-Draper law, or only the light that is observed by a substance can produce a photochemical effect. Stark-Einstein law of photochemical equivalence, it states that in a photochemical reaction, each molecules of the reacting substance absorbs single photon of the radiation causing the reaction. Uh, Only observed light radiation are effective produce a photochemical chemical reaction is the Grothus-Draper law, and the Stark-Einstein law in photochemical reaction. Each molecule of the reacting substance absorbs single photon of the radiation causing the reaction and is the activities from the form of products. The one photon of light is absorbed by reacting molecule, an excited molecule, and product molecule. Molecule A absorbs a photon of radiation and gets activated. The activated molecule then decomposed to build B, could say the same thing in the equational forms as A absorbs a photon of light in excited state and produces the B product. Also, we can write A as V and excited and produce B. B is the frequency of light is Planck's constant. The quantum energy absorbed per molecule equal as V equal to N as V. Equation 2 is the quantum energy absorbed per molecule and Avogadro's number. The quantity of energy is absorbed per mole of substance is called Einstein. V equal to C over lambda, C velocity of light, lambda wavelength. From equation 2 and 3, we can write E equal to NHC over lambda. Equation 4, N is the Avogadro's number, 6.023 10 to the power 23, as Planck's constant, 6.26 10 to the power minus 27 arc per second, C velocity of light, 3 into 10 to the power 10 cm per second. So E equal to, we can write this value. So this equation 5 indicates that energy per Einstein is inversely proportional to the wavelength of radiation. So E equal to 2.85 10 to the power 10 over lambda calorie per mole. It is evident from the 6 that the numerical value of Einstein varies inversely as the wavelength of radiation. The higher the wavelength, the smaller will be the energy per Einstein. The primary and secondary process of photochemical reaction, the reaction which is produced directly by the absorption of light, is called the primary photochemical process, and the secondary photochemical reaction is thermal reaction, which is of course subsequent to primary photochemical reaction. This is the hydrogen bromide in absorbed light. This is the dissociated hydride and bromide in the primary reaction. And again, this hydride ion reacts with the hydrogen bromide to produce hydrogen gas in the bromide secondary reaction. Also, this bromide ions combine to form bromine molecule secondary reaction. In photochemical reaction, the process are broadly divided into primary process and secondary process based on the sequence of events after light absorption. Primary process. This occur as the direct result of the absorption of light by the molecules and involve initial electronic excitation. They include absorption of photons. Molecules absorb light energy, which promotes an electron from the ground state to an excited state. Example, A real absorbs light and excited, where A is the molecule, H is the Planck's constant, and B is the frequency of light, and S star is the excited state. Excitation of electrons, the absorbed energy leads to transitions within the molecule, singlet or triplet excited state. A primary photochemical reaction, the excited molecules may undergo a chemical change such as dissociation, isomerization, and or electron transfer, for example, photodissociation. So AB star A plus B. A secondary process, this involves the subsequent reaction of the excited molecules or products formed in the primary state. They include relaxation, the excited molecules returns to the ground state emitting energy as heat or light, fluorescence or phosphorescence. Energy transfer, the excited molecule transfers energy to the other molecules or surroundings. Chemical reaction of excited products, the products of the primary process participate in further reaction. For example, in photosynthesis, light energy absorbed by chlorophyll leads to the splitting of water, followed by the secondary process that produce glucose. Formation of stable products, the intermediate species formed in the primary process react further to form stable chemical products. Example, photochemical reaction of chlorine and hydrogen chloride, formation of chlorine atoms. Secondary process, chlorine reacts with hydrogen and hydrogen chloride, and hydrogen reacts chlorine and hydrogen chloride propagation. Quantum yield or quantum efficiency, the number of molecules reacted or formed for photons of light observed is called quantum yield and denoted by phi. Phi equal number of molecules reacted or formed over number of photons observed. If phi equal to 1, that is one molecule is decomposed per photon, obeying the Einstein law. If phi is the greater than 1, the reaction has high quantum yield. If the phi is the less than 1, the reaction is to low quantum yield. Photochemical reaction in this case, quantum yield can measure how many molecules react per photon observed. For example, in photosynthesis, quantum yield refers to the efficiency of converting the light energy into chemical energy. Fluorescence of phosphorescence, quantum yield refers to the efficiency of photon emission compared to the photon absorption. For fluorescence, equal to number of photons observed over number of photons emitted. Thermoluminescence, it is the emission of light from the some minerals and certain other crystalline materials, and when it is called thermoluminescence. Heating the substance are 450 degrees Celsius and higher enables the trapped electrons to return to their normal position, resulting in the release of energy. Example, ceramics, bricks, etc. Chemiluminescence, the emission of light is a result of chemical reaction at ordinary temperature is called chemiluminescence. That light emitted is called cold light. The Now, it occurs when the chemical reaction creates an electronically excited state in a molecule, which then emits light as it returns to the ground state. Allophosphorus produces cool light on exposure to air at room temperature. Fairly glow in darkness due to the oxidation of luciferin in presence of enzyme in chemiluminescence reaction. The energy Chemiluminescence reaction, the energy is released by reaction which makes to excite the product. The excited molecule gives off its excess energy as visible light, which is reverting to the ground state. Catalysis of substance which alter the rate of chemical reaction but itself remains the chemically unchanged at the end of the reaction is called catalyst or catalytic agent, and phenomenon is called catalysis. Catalysis of catalysis and evident from above definition. A catalyst may increase or decrease the rate of reaction, which is classified as below. Positive catalyst, a substance which accelerates the rate of chemical reaction without undergoing any chemical change, is called positive catalyst, and phenomenon is called positive catalysis. For example, potassium chlorate, in presence of catalyst manganese dioxide, increases the rate of reaction. Negative catalyst, a catalyst which decrease the rate of chemical reaction, is called negative catalyst, and phenomenon is called negative catalysis. For example, in the oxidation of chloroform in presence of ethanol, it decreases. Autocatalysis, when one of the product of the reaction itself acts as a catalyst for the reaction, the Then source product is called autocatalysis and the phenomena is called autocatalysis. Example, hydrolysis of ester in acidic medium is an autocatalysis reaction. Induced catalysis, when a reaction catalyzes the other reaction, the phenomenon is known as induced catalysis. For example, sodium sulfide oxidizes in air changing to sodium sulfate, but sodium arsenide does not. When both are mixed together, sodium sulfide and the sodium arsenide both oxidize in air and produce sodium sulfate and the sodium arsenate. Types of catalysis, there are two types of catalysis in homogeneous and heterogeneous catalysis. Homogeneous catalysis in which the reactant and catalyst is in the same phase. Such type of catalysis is called homogeneous catalysis. This type of catalysis can occur in the gas phase or in the liquid phase. One-phase homogeneous catalysis, for example, sulfur dioxide in water in presence of nitric oxide produces sulfur trioxide. Is the catalyst and the reactants products are the similarly carbon dioxide and oxygen, carbon dioxide, the catalyst nitric oxide, all are in the gaseous phase. Liquid phase homogeneous catalysis, some example, hydrolysis of ester in presence of acid. For example, ethanoate in the water and acid. These are the liquid. Heterogeneous catalysis, the catalyst in which the catalyst is different physical phase from the reactant is known as heterogeneous catalysis. In this catalysis, reactants are in gas phase, while the catalyst is in the fluid phase. This type of catalysis is also called contact catalysis because this reaction occurs by contacting of with the catalyst surface. For example, nitrogen and hydrogen reacts to produce the ammonia, but catalyst is the iron. A catalytic promoter activity of catalyst can be increased by addition of small quantity of second material. The second material is called promoter or catalytic promoter or activators. The substances which themselves are not a catalyst but promote the activity of a catalyst in a chemical reaction are called catalytic promoters or activators. For example, molybdenum promotes the activity of the iron catalyst in the synthesis of the ammonia. Functions of catalytic promoter. The functions of promoters can be explained on the following headings. Change of lattice spacing. Promoters occupy in the interstitial position of the catalyst so that lattice spacing of the catalyst is increased. The bond between the adjacent molecule of reactant on the surface of the catalyst is also increased and bond is weak, so the bond break easily, which makes the reaction go faster. Promoters increases the peaks and the cracks on the surface of the catalyst, which helps to accelerate the rate of reaction. Catalytic poison, the term poison refers to the impurities present in the reaction system that destroys the efficiency of the catalyst. The substance present in the reaction system or along with the catalyst as the impurities which destroys the activity of catalyst is called catalytic poison or inhibitor or deactivator. Catalytic vanadium pentoxide or a platinum in the reaction of sulfur dioxide and oxygen to produce sulfur trioxide. Conversion is the 98% sulfur dioxide converted to sulfur trioxide. But in case of presence of hydrogen sulfide, it's the poison. Functions of catalytic inhibitors. Catalytic inhibitors, also known as the catalyst poisons, are substances that reduce or completely suppress the activity of catalyst in the chemical reaction. There are the following functions of the catalytic inhibitors or poison. The inhibitors exist on the surface of catalyst, which hinder the further adhesion of reactant molecule to the surface of the catalyst and actively or catalyst decreases. The inhibitor may combine chemically with the catalyst present in the reaction system and decrease its activity. Preventing the undesired reactions, catalyst inhibitors are used to block side reactions that might otherwise occur in the presence of the catalyst. For example, in hydrocarbon processing, inhibitors are added to prevent unwanted polymerization reaction. Regulating reactions rates the reduce the reactivity of catalyst to slow down the reaction for better control and precision in the industrial process. For example, in ammonia synthesis, small amounts of inhibitors like water or oxygen can help to optimize the reaction rate. Protecting the catalyst, some inhibitors temporarily deactivate the catalyst to protect them from the degradation of falling caused by the impurities in the reaction medium. Okay. Some inhibitors temporarily deactivate catalysts to protect them from the degradation or falling, that is the unwanted accumulation or deposition of the materials such as dust, rust, carbon or chemical residues caused by the impurities in the reaction medium. For example, sulfur compounds acting as the reversible inhibitors to protect the platinum catalyst in fuel reforming. Improving selectivity by inhibiting the catalytic sites responsible for undesired reactions, inhibitors can improve the selectivity of the main desired reaction. For example, in ethylene polymerization, inhibitors may target sites leading to the branch polymer formation. Research and analysis inhibitors are used in the experimental setups to study the mechanism of catalytic reactions by selectively blocking certain pathways. For example, using carbon monoxide to study surface interaction in hetero uh, aqueous catalytic, heterogeneous catalysis. Reducing poisoning in certain case inhibitors bind to impurities or contaminants that would be otherwise poison. The catalyst effectively acting in the sacrificial agent. For example, adding the chelating agents to bind the heavy metals before they uh, is the catalyst. Types of inhibitors, competitive inhibitors competing with the reactants for the active sites of the catalyst. Non-competitive inhibitors binding to a different parts of the catalyst, altering its shape or functionality. Irreversible inhibitors inhibition permanently deactivating the catalyst through strong chemical bonding. Characteristic character of catalysis. A catalyst remains unchanged in mass and chemical composition at the end of the chemical reaction. A catalyst is more effective when it is the finely divided. A catalyst is specific in nature. For example, ethanol, in presence of alumina and copper, it produces dehydration in case of the alumina, but in copper and removal of hydrogen, that is the dehydrogenation. Similarly, an formic acid, in case of alumina, it is the dehydration, and copper dehydrogenation. A catalyst does not affect the equilibrium system. The catalyst catalyze the both forward and backward reaction to the uh, some extent in the reversible reaction and thus have no effect to the equilibrium constant. A catalyst has the optimum pace at which the action of catalyst is maximum. A small quantity of catalyst is generally sufficient to catalyze almost unlimited reaction. For example, in the decomposition of hydrogen peroxide, 1 gram of colloidal platinum can catalyze 10 to the power 8 liters of hydrogen peroxides. In the sum of the reaction in the rate of reaction is proportional to the concentration of the catalyst For example, the acid and alkaline hydrolysis of ester, the rate of reaction is proportional to the concentration of hydrogen and hydroxide ions. In Friedel-Crafts reaction, anhydrous aluminum chloride is required in a relatively large amount to extend 30% of the mass of benzene. In certain heterogeneous reactions, the rate of reaction increases with the increase of area of catalytic surface. The catalyst cannot initiate the reaction. The function of the catalyst is to alter the speed of reaction rather than to start it. And catalytic promoters substances which themselves are not catalysts, but when the mix in small quantities with the catalyst increase their efficiency are called as promoter or activators. For example, in Haber's process for the synthesis of ammonia, traces of molybdenum increases the activity of finely divided iron, which acts as the catalyst. In the industrial synthesis of methyl alcohol, methanol from the water gas mixture of hydrogen carbon monoxide and carbon dioxide, zinc oxide serves as the main catalyst, while the chromic oxide acts as the promoter. The process can be summarized as follows. In the hydrogenation of oils, the activity of catalyst nickel increases on adding a small amount of copper. A reaction on hydrogenation of oils. Catalytic poisons, substances which destroy the activity of catalysts by their presence of known as the catalytic poisons. For example, the presence of traces of arsenic oxide in the reacting gases reduce the activity of platinized asbestos, which is used as catalyst in the contact process for the manufacture of sulfuric acid. The activity of iron catalyst is destroyed by the presence of iron sulfide or carbon monoxide in the synthesis of ammonia by Haber's process. The platinum catalyst used in the oxidation of hydrogen is poisoned by the carbon monoxide. Change of temperature alters the rate of catalytic reaction as it does not. Thus, for the same reaction in the absence of catalyst by increasing the temperature, there is an increase in the catalytic power of the catalyst. But after a certain temperature, its power begins to decrease. A catalyst has thus a particular temperature at which its catalytic activity is maximum. This temperature is termed as the optimum temperature. Positive catalysis stores the activist energy according to the collision theory. Reaction occurs on account of the effective collision between the reacting molecules. For the effective collision, it is necessary that the molecules must possess a minimum amount of energy known as the activation energy. After the collision, molecules from an activated complex which dissociate to yield the product molecules, the catalyst provides a new pathway involving the lower amount of activation energy. Thus, the large number of effective collisions occur in the presence of catalyst in comparison to the active collision, and same temperature is absence of catalyst. Hence, the presence of catalyst makes the reaction to go faster. Function of catalyst, when a catalyst is used in the chemical reaction, it lowers the activation energy of the reactant system, providing new part. Thus, large number of effective collision occurs in the presence of catalyst and rate of reaction becomes higher. Theory of catalysis, there are the two main theories of catalysis. There are the intermediate compound and formation theory and absorption of theory. And generally, intermediate compounds formation theory is applicable in case of the homogeneous catalysis, and absorption theory is applicable in case of heterogeneous catalysis. Intermediate compound formation theory, according to this theory, catalyst form is the intermediate compound with one of the reactant in order system. This form intermediate compound is highly reactive, which react with the second reactant and gives the product, and can be explained as A plus B gives product, C is the catalyst, and A, B, and reactants. The postulated steps in the reaction according to this theory: A plus C as intermediate and SCB products, C catalyst. In specific examples, sulfur dioxide and oxygen reacts in the presence of nitric oxide, produces sulfur trioxide. In nitric oxide and oxygen gives nitrogen dioxide, and nitrogen dioxide and sulfur dioxide gives sulfur trioxide in nitric oxides. Absorption theory. This absorption theory is mainly applicable in case of heterogeneous catalyst contact catalysis. According to this theory, reactant molecules are absorbed adds on the surface of the catalyst and gives the product. Generally, there are the four steps put provided for the heterogeneous catalysis, and its adjacent reacting molecules on the surface of catalyst and formation of the activated complex between the adjacent molecule on the surface of catalyst, decomposition of activated complex into products on the surface of the catalyst, decomposition of products molecules from the catalyst surface. Let us consider a general catalytic reaction as hydrogenation of 18 in presence of nickel catalyst. Enzymatic catalysis. Enzymes are protein molecules which act as the catalyst to speed up the organic reaction in living cells. The catalyst brought about by the enzyme is known as the enzyme catalysis. The enzyme is the produced in the particular living cells to catalyze a reaction occurring in that cell, so that enzymes are specific in nature. Conversion of starch into maltose by the diastase, and conversion of dextrose into ethanol by xylase, conversion of maltose into glucose by maltase. Mechanism of enzyme catalyst. Mechanism enzyme catalyst reaction can be explained on the basis of lock and key theory. This theory purposes that as a particular lock can be opened by the particular key, in the same way particular enzyme act on a particular substrate. The long chain of the enzyme protein molecule are coiled on each order to make a rigid colloidal particle with cavities on its surface. Thus, the substrate of molecules which have complementary shape fit into these cavities just as the key fit into lock. The enzyme form an activated complex with the substrate, and decomposition gives products. For the figure lock and key model in enzyme catalysis, characteristic of enzyme catalysis. Enzyme generally accelerates biochemical reaction by reducing the energy required in the activation energy. Energy do not alter the amount of products. Enzyme retain their identity at the end of the reaction. Enzymes are highly specific in nature, and the enzymes catalyst reaction as on the optimum temperature in which the catalytic of enzyme is the maximum. The rate of reaction decreases as the temperature increases or decreases from the optimum value. The extreme temperature of the enzyme gets decreases and loses its identity. The figure variation of rate of enzyme catalyst reaction in the optimum. This point is optimum point in this reaction. 40 degrees Celsius is the optimum temperature, and catalytic activity of enzyme is the increases in presence of enzyme and completely destroyed. An enzyme catalyst reaction also gives the optimum pH value in which the catalytic activity enzyme is the maximum. The rate of the reaction decreases as the pH is increases or decreases from the optimum value. Variation of the enzyme or catalyst in the optimum pH. This is this range, the optimum pH. Acid catalysis based reaction, and ethanol reacts with acid and intermediate complex, and intermediate complex again reacts with the ethanoic acid and produces the ester. In acid catalysis, the catalyst donate a proton to one of the reactant to form the intermediate compound, which undergoes the deprotonation reaction with other reaction and gives the product with the regeneration of proton. In the base catalysis, the hydroxide ion form a strong base or any Boston base accept a proton from a reactant to form the intermediate compound which react or decompose to give the product, and hydroxide to back to regenerate. Okay, it's all about uh, photochemistry and catalysis under BSc second year, Institute of Science and Technology, Trinidad University. Best of luck, and thanks for watching, and request you all like, comment, share, and subscribe. Thank you for your patience. That is now. Bye bye. See you again.